A seemingly inert paperclip, left outside, orchestrates a complex chemical dance with oxygen and water, slowly transforming its very structure. This mundane metal object reveals a fundamental chemical principle governing the very food we prepare and consume daily. You never considered the humble paperclip a hotbed of molecular activity, yet its surface engages in invisible reactions. Even the simplest metals around us continuously undergo intricate chemical transformations, often without our conscious awareness of the process. Understanding these subtle changes, like the slow degradation of a paperclip, unlocks profound secrets about the food in your kitchen. Why care? These precise chemical reactions dictate your food's taste, texture, nutritional value, and even shelf life. At the heart of many transformations lies oxidation, a fundamental process where molecules lose electrons, often triggered by oxygen exposure. Mastering the principles of oxidation and other cooking chemistry will profoundly enhance your culinary skills and understanding of ingredients. Consider a common kitchen scenario: a vibrant green sliced avocado quickly turning unappetizing brown before your eyes. This visible change isn't magic, but a clear demonstration of powerful, invisible chemical reactions happening right on the food's surface. We constantly interact with these chemical marvels, often without realizing their profound influence on our daily meals and eating experiences.
Delving into the molecular world of food reveals how everyday cooking is truly a fascinating, hands-on chemistry experiment in action.
Consider that simple paperclip. Its experiment in action consists mostly of iron atoms, eagerly awaiting interaction with its surrounding environment. Exposed to air's oxygen and water, iron atoms begin an electron transfer process, forming new, stable bonds. These iron atoms essentially donate their electrons to the oxygen, becoming positively charged ions in a classic oxidation reaction. The visible outcome of this complex molecular exchange is the reddish-brown substance we commonly recognize as rust or iron oxide. But this isn't just about rusty metal. Precisely analogous chemical principles govern the quality and transformation of our everyday food. Imagine a freshly cut apple turning brown, or cooking oil developing an unpleasant, rancid smell after prolonged exposure to air. These familiar deteriorations are also prime examples of oxidation reactions, just involving complex organic molecules instead of simple iron. For instance, enzymes like polyphenol oxidase in apples react with oxygen, creating those undesirable brown pigments on the fruit's surface. Similarly, unsaturated fats in cooking oils react with atmospheric oxygen, forming off flavors and unpleasant odors.
This process, called lipid oxidation, breaks down healthy fats into smaller, volatile compounds, diminishing nutritional value and palatability.
Think of it like a molecular chain reaction. One oxidized fat molecule can trigger the breakdown of many more. Until you volatile hear what comes compounds next. Nutritional value and chemistry palatability becomes even more intricate and beautiful when we introduce the element of heat. The Maillard reaction, for example, is not simple oxidation, but a complex dance between amino acids and reducing sugars under heat. This reaction creates hundreds of new flavor and aroma compounds, responsible for bread's crust or meat's savory sear. Consider the delectable golden brown crust on roasted vegetables, or the rich complexity of a perfectly grilled steak. Different temperatures and pH levels can significantly alter the specific compounds formed, leading to a vast array of unique flavors. Caramelization represents another heat-driven transformation, where sugars alone break down and rearrange into a rich spectrum of sweet compounds. This process, occurring at higher temperatures than Maillard, creates the deep amber hues and nutty, buttery notes in caramelized onions.
Imagine these reactions like tiny molecular construction sites, constantly building, breaking, and rearranging molecules into different structures. Proteins, for instance, denature and coagulate when heated, changing from a fluid liquid like egg white into a solid, opaque mass.
This structural change traps air and water, leading to fluffy baked goods or the firm consistency of a cooked egg.
Starch molecules absorb water and swell, a process called gelatinization, transforming raw flour into the thick, smooth texture of gravy.
And then something unexpected happened. Sometimes these same powerful reactions cause undesirable outcomes, leading to food spoilage. We often use techniques to actively prevent or slow these detrimental chemical changes, ensuring our food remains safe and appealing. For example, adding an acid like lemon juice to cut fruit inhibits the browning enzymes, preserving its fresh, vibrant appearance longer. Antioxidants, found naturally in many fruits and vegetables, act as molecular electron sponges, preventing harmful oxidation reactions from occurring. These protective compounds essentially sacrifice themselves, absorbing rogue electrons before they can damage essential food components. Freezing food dramatically slows down virtually all chemical reactions, including oxidation, thereby extending its usable shelf life significantly. Even packaging plays a crucial role, creating barriers against oxygen and light, common triggers for undesirable chemical transformations in food. Consider covering leftovers tightly. You are actively engaging in food chemistry. Preservation is fundamentally a method of manipulating these intricate chemical and physical processes. Every cooking technique, from boiling to baking, is fundamentally a method of manipulating these intricate chemical and physical processes.
Understanding these underlying mechanisms allows you to predict how ingredients will behave and consciously control the final outcome.
It's like having a secret language for food, where every ingredient speaks volumes about its chemical potential. Even the texture of pasta changes due to starch chemistry, becoming al dente through controlled hydration and structural rearrangement. This intricate molecular choreography happens constantly, influencing everything from a perfectly baked cake to a crispy fried potato chip. Understanding these chemical processes directly determines how long your food remains fresh and flavorful in your pantry or refrigerator. They also create the incredibly delicious aromas, textures, and tastes that elevate simple ingredients into truly memorable culinary experiences. Mastering the basics of cooking chemistry empowers you to control these reactions, transforming you into a more intuitive and effective cook. This knowledge profoundly matters, from preventing premature spoilage to enhancing the rich, complex flavors of cooked dishes. Professional chefs, for example, they might interactions to sear or achieve specific steak at high textures and heat for the maximize Maillard flavor reaction development. They might enter or add lemon juice to apples, slowing enzymatic browning effectively. Knowing the science means you can intentionally choose to roast vegetables instead of steaming them for specific flavor benefits. It allows you to troubleshoot cooking mishaps, understanding why a sauce broke or bread didn't rise as expected. This hidden, intricate chemistry profoundly shapes our culinary experience, from farm to fork, meal after delicious meal. It truly transforms raw, simple ingredients into nourishing, delightful meals that satisfy both body and soul with incredible precision. The simple act of cooking is not merely following a recipe, but actively engaging in a complex, beautiful chemical dance. If you found this exploration of food chemistry fascinating, subscribe for more incredible scientific journeys and discoveries. And let me know in the comments below what aspect of cooking chemistry truly fascinates you most. If you found this exploration of food chemistry fascinating, subscribe for more incredible scientific journeys and discoveries. And let me know in the comments below what aspect of cooking chemistry truly fascinates you most.